Mm. Mhm. 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 Good. 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 Good.
ஐயய்ய! நான் மட்டும் தான் இருக்கனா?
Good. Good.
Good evening, students. We'll start the lecture. So this week we will solve some problems from batch and fed batch bioreactor design. So let's start. So the first problem is glucose is being used for the production of E. coli. In a 1200 meter cube bioreactor, and the 60 gram per liter of glucose is being fed into the system with a substrate conversion of 95% in the process. the biomass yield from the substrate is 0.55 gram per gram. Assume that the specific growth rate is approximately equal to mu max, which is given as 0.5 R inverse. For this batch mode of operation, the initial cell concentration is 0.1 gram per liter and the downtime between the batches is 20 hours. So we have been given set of 5 questions. Let's start solving one by one actually. So let's start to write down the given values. Yeah, so it is given that our volume is 1200 meter cube and what else is given? S naught is given as 60 gram per liter and it is also given as 95% of substrate is being consumed or converted. So 95% is converted means 5% is remaining. 5% of the S naught which was given is remaining, right? So which means that 5% of your S naught is equal to SF, which means 0.05 into 60 gram per liter, which is nothing but 3 gram per liter. And what else is given? Mu is equal to mu max is given as 0.5 hour inverse and sorry, X naught is given as 0.1 gram per liter and the downtime between the batches is given as 20 hours, means in between two batch of running the reactor there is a downtime for cleaning, maintenance, everything of around 20 hours. So the time for downtime is 20 hours. What else is given? And it is also given that your biomass yield from the substrate, that is Y-axis, is given as 0.55 gram per gram. So we have written down all the given data. So as we discussed in the last class, the batch time formulas you would have remembered. So let's start writing the batch time for formula. 1 by mu max ln of 1 plus y xs by x naught S naught minus S. So substitute all the values which are known. So 1 by 0.5 ln of 1 plus 0.55 divided by 0.1, 60 minus 3. So if we do the calculation, the answer will come around. How much it will be? 0.55 divided by 1. 55 divided by 1.1. 0.1 is 5.5. 1 plus 5.5 into 57. 57 is 31. Ln of 314.5. Coming around 11.501. 1 hours. So your batch time is calculated as 11.5 hours. So what was asked next? The total mass of cells produced per batch in kg. Total mass of cells means what? It is XF, right? That too they want in terms of kg. So what is the formula for calculating X? You have We all know that ln x by x naught is equal to mu max into T. If we give the notation of xf to this and rearrange the equation, it will become x naught into e power of mu max into T. So this means x naught we know 0.1, e power of mu max is given as 0.5, and we know the batch time is 11.5. So we can easily calculate the xf. So how much is the value? The value is coming around, it's coming around 31.4 gram per liter. So now we know the value of xf. We have to calculate in terms of kg. For that, what we have to do, we have to multiply with respect to volume. So how do we do that? We have to minus the initial inoculum and multiply it by volume. So 31.4 minus 0.1 into what is the volume? Volume is 1200 meter cube. So 1 meter cube is around 10 to the power 3 liters. So let's write as in terms of liter. So if you do this, the value of x will be around how much? 1.3 into 1200 into 10 to the power 3. It should be around 31.3 into 1200 is 37560 3 grams. It's nothing but 37560 kg. Okay. So what is the question number C? Question number C is to calculate total number of batches in a year. So now we know how much amount of cells are being produced per batch, and we know the batch time and we know the downtime. Now we have to calculate total number of batches which can be run in a single year. So for that, what we have to do, we have to find the total time for running a batch. So the T total is batch time plus downtime, which is 11.5 plus 20 hours. So the total time is 31.5 hours. So we know in a year we have 365 days, which is how many hours are there? 365 into 24, it's around 8764 hours. So it's around 278 runs per year. So it's around 278 runs per year. So what is the question D? It is the total mass of cells produced annually during the batch culture. So annual, we have calculated per batch in terms of kg. Now we want in terms of um, how much will be produced annually during the batch culture in terms of tons per year. So we can calculate that also. So to begin with, annual production is equal to total biomass produced into runtime, like, or number of runs, which is 37560 kg is produced into 278 runs per year. Multiply around 10441 kg per year. But we know that 1 ton is 10 to the power 3 kg. So how it can be written? Can be written as 1 ton per year. So this is the annual biomass production. So what else is asked? If this is the annual biomass which will be produced for the values which they have given. So now it's been asked that if the desired annual biomass production is set as 15,000 tons per year only, what should be the volume of the reactor in terms of meter cube? So now they have given this value and they are telling that it is to be set as 15,000 tons per year. How much would be the reactor volume? So for that, we'll use the same formula, but we know the annual production, which is 15,000 ton per year. And the number of runs we know, and we don't know the exact weight. It's the biomass which will be produced. To calculate this, just cross multiply. So 15,000 divided by 278, which will give you around 53.95. So approximately 54 tons. So from here, 54 tons per year is per batch is required. So now from here you calculate the volume. So we know that the X total biomass, we can calculate it from XF X naught into V, which is we know already, into V. So it will be 54 divided by 31.3 gram per liter. Converting it into grams for easier understanding. Should be 1.72 into 10 to the power 6 liters. So we know that 1 meter cube is 10 to the power 3 liters. We want the answer in terms of meter cube. So the answer would be 1.72 into 10 to the power 3 meter cube. So for the production of 15,000 tons per annum, 15,000 tons per year, with the downtime of 31, with the total time of batch time to be around 31.5 hours, the volume of the reactor required is around 1.72 into 10 to the power 3 meter cube. Okay, let's go to the next question. So this question is about fed batch operation. So the question number 2 is Nicotiana tabacum cells are cultured to high cell density for production of polysaccharide gum, and the reactor used is a stirred tank reactor containing initially 1000 liters medium. So the maximum specific growth rate of the culture is 0.18 day inverse, and the yield of the biomass from substrate is 0.5 gram per gram. The concentration of growth limiting substrate in the medium is 3%. The reactor is inoculated with 1.5 gram per liter of cells and operated in batch until the substrate is virtually exhausted. So the medium flow is then started at a rate of 4 liter per day. The fed batch operation occurs under quasi steady state conditions. So you are asked to uh, identify or estimate the batch culture time. We have already done it, so we'll follow the same protocol, and the final biomass concentration. So we have already solved this in the previous problem. Same way we will solve it again. So the question B is fed batch operation is carried out for 40 days. What is the final mass of cells in the reactor? After 40 days of fed batch, what is the final mass which will be remaining inside the reactor? And C is the fermenter is available 275 days per year with a downtime between runs of 24 hours. And how much plant cell biomass is produced annually? This is the question. Let's start solving it by writing down the given values. So what is the given values? So let's start writing by jotting it down. So the reactor used is the stirred tank reactor, and initially they are telling that the volume was 100 liters of medium. Maximum specific growth rate is mu max is around 0.18 day inverse, and the yield of biomass y-axis is 0.5 gram per gram. Concentration of growth limiting substrate in the medium was in the 100 liter medium, it was 3% weight per volume, means 3 gram per 100 ml, which means 30 gram per liter. Then what else is given? The reactor is inoculated with the inoculum. Initial inoculum they have given, it is X naught, which is 1.5 gram per liter, and they are telling that after the medium substrate is exhausted, the flow rate is then started at a rate of, they have given the rate at which the substrate is fed. That is 4 liter per day. So first, let's calculate the batch culture time and final biomass concentration as given in question A. So what is the formula? As we have been solving, the batch time is given as 1 by mu max ln of 1 plus 1 plus what y-axis divided by x naught and s naught minus sf. So which is, what is the value of mu? Mu is given as 0.18 day inverse. So 1 by 0.18 ln of 1 plus 0.5 is the y-axis, and x naught is 1.5, s naught is 30, and we know that substrate is getting limited at the end of the batch. So let's keep it as 0. If you do this, if you solve this equation, how much will be the answer? Point 0.5 divided by 1.5 is 0.33 into 30 is 10. This one 11. Ln 11 is 0.1 divided by 0.9. It's coming around 13.32 hours. Or how, what time? Sorry, it is days. So it was also asked to give us the total biomass concentration. Final biomass concentration is Xa. So we know Xf is equal to X naught e power of mu max into T. So X naught is given as 1.5 gram per liter. T mu max is 0.8, and we calculated the time, which is around 13.32. If you do this, what would be the answer? It would be around 16.4 gram per liter. Okay. Now we have completed part A of the question. So what from part A, what we calculated, the batch culture time is 13.32 days and the final biomass concentration is 16.4 gram per liter. What is asked in the second? So the fed batch operation is carried out for 40 days, and what is the final mass of cells in the bioreactor? So after the batch time of 13.32 days, another 40 days of fed batch is going on. So the mass of the cells, how do we put? So after batch is completed, now after 13.3 days, we are giving the feed in and letting it for 40 days. The feed flow rate was at 4 liters per day. So the mass of cells at the start of the wet batch operation is equal to the final batch cell concentration multiplied by the initial medium volume. So it is nothing but X naught is equal to, which is the mass of the cells at the start of the fed batch operation, is equal to the final batch cell concentration, which is when you finish the batch, what is remaining is the final batch cell concentration into the initial medium volume. So if you do that, X naught is equal to, will be given as 16.4 gram per liter into 100 liter is the initial volume. So 1640 grams is the X naught. So to calculate the final mass which is remaining after 40 days of fed batch culture condition can be given as initial substrate, the flow rate into fed batch time. I hope that you guys have gone through the fed batch design equations taught in this week. So the X naught is 1640 gram plus YX is 0.5 gram per gram into initial is 30 gram per liter into flow rate was 4 liter per day into fed batch time is 40 days. If you do the calculation, please let's solve and find the answer for this question. So what would be the answer? 0.5 into it's 0.5 into 30 into 4, 60, 60 into 40 plus 1640. It's 4040 grams, nothing but 4.04 kilograms. So the final biomass concentration for the final mass of cells Remaining after 40 days of fed batch culture would be 4.04 kg. Let's calculate C. What is C? The fermenter is available only during 275 days per year. The downtime is 24 hours. And you are asked how much plant cell biomass is produced annually. So with this time period, we have to calculate how much of the biomass will be produced for an entire year. And it should be noted that the fermenter is available only for 275 days per year. So for this, what we have to start with, uh, so to calculate the biomass produced per each run, it means that is equal to the final biomass. We know that it was around 4040 grams or 4.04. So it is the biomass which is at the end of the fed batch minus the initial inoculum used for inoculating the reactor multiplied by the volume. Means that 1.5 was the X naught into 100 liter. That's nothing but 150. So it is around 0.4040 minus 150 is 3890. Just 3890. Which is nothing but 3.89 kgs. So the mass of the cells produced in each reactor run is equal to the final biomass, which is the final biomass of the fed batch minus the initial biomass used for inoculum. So we know the total, this is the biomass produced per each run. We know the total time is batch time plus fed batch time plus time for downtime. So what was the batch time we calculated? The batch time is around 13.32 and we know the downtime is 24 hours and the fed batch time is given as 40 hours. So if we do the calculation, 13.3 plus fed batch is 40 days plus downtime is 24 hours. Let's convert it to day as everything else is in day. So 1 day is equal to 41 plus 54.3 days. And it's also given in the question that in a year the fermenter is available. Okay. Fermenter is available only for 275 days. So this is the number of days it takes to run one single run. So to calculate the number of runs, 275 divided by number of days it takes to run a single run. So given as 5.06 runs. Approximately 5 runs we can make. What is asked? So we have now found how many runs can be done. So we should calculate now how much plant cell biomass is produced annually. To calculate that, what we have to do? So like we did in the last problem. So the biomass produced per year equal to total biomass produced into run. So what was the total biomass we have calculated? It is 3.89 kg, 3.89 kg into 5.06, or you can take it as 5 runs. So what would be the answer? 5.06 into, it's around 19.6, approximately 19.68. So we can put it as 19.7 kgs. So the biomass produced per year would be 19.7 kgs. So let's move to the next question. Please read the question and I'll give 2 minutes to write down the given conditions. So I'll read the question. 7-chlorotetracycline is produced by high cell density cultivation of engineered strain of Streptomyces aerophaciens in fed-batch mode with the intermittent addition of fructose solution to the culture medium. So here the fructose solution is your feed, your substrate. So the initial culture volume at quasi-steady state is initial volume is V0 is equal to 300 liter, and the fructose containing nutrient solution is added at a flow rate of F is equal to 100 liters per hour. So the fructose concentration in the feed solution and the initial cell concentration is S0 is equal to 400 gram per liter, and X0 is given as 15 gram dry weight per meter. Assume that the organism follows monad kinetics, and the kinetics and the yield coefficients of the organism are also given. But this mu max is 0.2 R inverse, Ks is given as 0.5 gram per liter, and the yield with respect to the fructose or the substrate is given as 0.3 gram dry weight per gram of fructose. So you are asked to determine the culture volume at the quasi steady state when time is 5 hours, what would be the culture volume? And B is the dilution rate D after 5 hours of this fed batch operation. C, determine the concentration of fructose, which is the substrate, at time is equal to 5 hours at the quasi steady state. D, determine the total amount of cells at quasi steady state when time is 5 hours. Determine the concentration of cells at quasi steady state when time is equal to 5 hours. You have to carefully see whether it is the total amount of cells, and there you are asked in the E question, it is concentration of cells in terms of gram per liter. And F, the question F is if QP is the specific product formation rate is 0.05 gram products per gram of cells hour, and P naught is the initial product concentration, which is given as 0.1 gram per liter. Determine the product concentration in the vessel or the reactor at time is equal to T is equal to 5 hours in terms of gram per liter. Please read the question and first start writing the given values. We'll take 2 minutes and then start solving the problem. So let's start writing the given values. So what is given? V naught is given as 300 liters. Feed flow rate is given as 100 liter per hour. substrate initial concentration is given as 400 gram per liter. Prasanna, you're talking? Hello. X naught is given as 15 gram dry weight per liter, and you are given mu max is 0.2 hour inverse. Ks is given as 0.5 gram per liter. Y-axis is given as 0.3 gram per gram. So now let's start calculating the culture volume at quasi-steady state. How do we start calculating it? Okay, let's start. Question A. So the culture volume, V naught is the initial culture volume, plus F is the flow rate, and T is the time. So you have been told that at time is equal to 5 hours, and V naught we know it is 300 liters, and F is given as 100 liter per hour, which means just substitution V is equal to 300 plus 100 liter per hour into 5 hours. So what would be the answer? 300 plus 500 is 800 liter. Simple. So V, which is the culture volume at quasi steady state when time t is 5 hours, is 800 liters. So the next question B is, they have asked the dilution rate, which is D, after 5 hours of this fed batch operation. What is D? F by V, which is F we know it is given 100 liters per hour, and V we just calculated it is 800 liters. So if we do the calculation, how much 100 by 800 is? It's around 0.125 hour inverse. Okay. So now the question number C is, determine the concentration of fructose at time is equal to 5 hours at quasi steady state in terms of gram per liter. So how do we start calculating? So we know that under quasi steady state condition, D, that is your dilution rate, will be approximately equal to mu. And according to mu, Monod's kinetics, and it is also told that the culture follows Monod's kinetic. So mu is equal to mu max S by Ks plus S, and we know that at quasi steady state D is approximately equal to mu, which means that mu is equal to D is equal to mu max S by Ks plus S. Now let's start forming in terms of so if we do this, S is equal to D into Ks divided by mu max minus D. So we have created a expression with respect to substrate at considering at quasi steady state D will be approximately equal to mu. So now you know the values of D, you know mu m, you can you know the value of Ks also, you can just substitute it. So if we do so, what would be the answer? We know that we just found that D value is 0.125, our inverse, and Ks is given as 0.5 gram per liter. Mu max is given as 0.2, our inverse, and 0.125, our inverse is our D. So if we do so, the answer would be, what would be the answer? It's around 0.83 gram per liter. This is what? This is the concentration of fructose at time is equal to T considering quasi steady state. And the fourth question is determine the total amount of cells at quasi steady state when time is equal to 5 hours. So how do we calculate total amount of cells? And again it is at quasi steady state. So at quasi steady state, and it is also given at it is a high cell density operating system. It is assumed that substrate will be final substrate concentration will be lesser than the initial substrate concentration. And also you have to apply D is approximately equal to mu. If you use this in the mass balance equation, then the same formula which we used in the previous question, which is X is equal to X naught plus Y excess S initial flow rate into time for fed batch. This will give you the amount of cells which will be produced at the quasi steady state condition. So X naught, how do we calculate? It is concentration into volume. So this X naught is calculated as X naught into V naught. Let's keep at time is equal to 5 hours. This also at time T is equal to 5 hours. Should not miss. So that is the case. X time is equal to 5 hours is X naught is what? X naught is given as 15 gram per dry weight liter, and Y axis is given as 0.3 gram dry weight per gram of fructose. SI is given as 400 gram per liter. And how much is the time for fed batch? It's given as 5 hours. So if we substitute everything which we know, 15 gram dry weight per liter into 300 liter, this is for X naught into V. Okay, we are substituting this here. Plus Y-axis is 0.3 into S I is 400 and the flow rate is 100 liter per hour into 5 hours. If we do this, what would be the answer? The answer is 15 in, sorry, 0.3 into 400 into 100. 3000 plus 15 into 300. 64,500 is known as 64.5 kg. So this is the total amount of cells at quasi steady state when time is 5 hours. So now you have to calculate the concentration of cells. So you have it in terms of grams. Now you can convert it into terms of gram per liter. For that, what you have to do? X total, this is our XT. XT at 5 hours. 5 hours divided by volume. So volume of the reactor was given, what we calculated. We have calculated that it is 800 liters. So is 64.5 kg or 64,500 divided by 800. 64,500 divided by 800 is 80.625. 80.625 gram per liter. This is the concentration of cells at time is equal to 5 hours. And here is the question F. This is about product, and you would have come across I hope you have gone through the lecture videos to understand how this formula has been derived. I'm not going to derive it again. Just so based on our product balance, which is done in your class sessions, P is P naught V naught by V QP into XM V naught by V plus this in terms of quasi steady state, so the term D is also included. So this XM we can replace it by what is the XM? Yield into concentration of substrate. So let's see what is given. P naught is given. P naught is given as 0.1 gram per liter, and QP is also given, which is 0.05 gram product per gram of cells. And we were asked to determine P. So let's substitute everything else. 0.1 into 300 liters. This is the initial volume, okay? And this is the volume after fed batch. So this we can write as QP 0.05 into y-axis is 0.3, and volume at the fed batch is SI. SI is after the feed is 400, and V naught is 300 by 800 plus D. D is 0.125 into time is 5 hours divided by 2 into 5. So solve this, we'll get the answer for P. So what would be coming? It would be, let's start finding out the answer. 300 divided by 800, 0.375 plus 0.125 675 0.5 0.3 into 400. 6 into 1.625 into 5, 8.75 plus 0.0 0.05 into 0.3 into 400. It's 300 divided by 800. 125 into 5 divided by 2. This 0.375 this point. So the concentration of your product is 20.6625 approximately. You can make it as 20.6, 20.7 gram per liter. So let's move to the next question. So we have been solving similar problems. So this would be, I think, easy for you as we have just solved the previous problem. So the penicillin is produced by penicillium chrysogenum in a fed batch culture with the intermittent addition of glucose solution to the culture medium. So the initial culture volume at quasi-steady state is V naught is given as 500 liter, and the glucose containing nutrient solution is added with a flow rate F is equal to 50 liter per hour. The glucose concentration in the feed solution and the initial concentration are given as S naught is equal to 300 gram per liter and X naught is given as 20 gram per liter. So the kinetic and yield coefficients are given as mu max is equal to 0.2, yxs is 0.3 and ks is given as 0.5. We have to determine the culture volume at t is equal to 10 hours. It is very similar to the previous problem where we have calculated the culture volume at time 5. Now we have to calculate the t is given as 10 hours. And this we know. And B is the concentration of glucose at time is equal to 10 hours, which is very similar to the which question? C. The same way how we solve C, and determine the concentration and total amount of cells at quasi-steady state when time is equal to 10 hours. So if you are following through the when I was solving the problem, you will be easily able to solve these questions. This is similar to the D and E of the previous question. The total amount of cells and the concentration of cells at quasi-steady state when t is equal to 5 hours. Here the time period is given as 10 hours. So first write down the given option given conditions and given values and try to start solving it. I'll also start solving. First, let's take a minute to write down the given values. Yes, Tejas, the volume of the culture volume is 1000 liters. You are right. How do we start solving? V is V naught plus FT. Tejas has given the right answer. So V naught is given as 500 plus we were given the flow rate as 10 hours. So if you calculate 500 plus 500, it is 1000 liters. Very good, Tejas. So what is the next question? How do we proceed to the next question? So how do what and all is necessary to calculate the quasi-steady state condition? D is necessary. So first we have to calculate D. The value of D is F by V, right? So F is what? It is already given, 50 liter per hour. And V is what? 1000 liters. So how much would be the value of D? The value of D is around 50 by 1000 is what? 0.05, our inverse. So from here we know the value of 0.05, our inverse. So what did we do to calculate the value of substrate concentration at quasi-steady state? S is equal to, we have derived an expression from the Monod kinetics and considering D is approximately equal to dilution rate at the quasi-steady state condition. This is the expression we derived. So we just have to substitute the values. So what are the values? D value is 0.05 and Ks is how much? 0.5 and mu max is given as 0.2. So let's substitute everything. If we do so, what would be the answer here? So the value of S would be, anybody solving? So the value of S would be 1.66 gram per liter. So what else you have been asked? Uh, okay, let me check my answer. Tejas has written 0.75. 0.5 into 0.05 is 0.025. This is 0.025 divided by 0.4 minus 0.05.15. Tejas, can you please check your answer? I'm getting 0.166 gram per liter. Anybody else is getting the same answer? It is 0.05, the value of D, into 0.5 divided by zero point 0.2 is your mu max minus D value. It's 0.05. Yes, Prasanna got the answer. Tejas, you check the answer, please. Just check where you missed anything. Any sign problem would be there, I think. Instead of multiplication, some minus sign, something. Please check, okay? Thank you, Tejas and Prasanna. So what is the C option? We have to calculate the concentration and the total amount of cells at quasi-steady state. How do we calculate? We have previously solved, right? The same formula here. X is equal to x naught plus y-axis SI into your flow rate at time 10. So we will write, I'll write down here for you. X is equal to x naught plus y-axis SI f into time for the batch. So we know this time is 10 hours only it's been asked for x naught at t is equal to 10 hours. This is also at t is equal to 10 hours. So how do we calculate the concentration? It should be multiplied by the volume of the feed, right? What it should be multiplied with? Volume of the feed or volume of the reactor? We should multiply with the initial culture volume, which is V naught is equal to, we did the calculation, right? X naught is equal to X naught into V naught. X naught at T is equal to 10 hours. So the initial concentration is 20 gram per liter. Now the volume is 500 liters plus your y-axis is how much? Y-axis is given as, F is given as 50 liter per liter. Y-axis 0.3. So, and initial cell concentration and the initial glucose concentration is, which is S naught, is given as Si or S naught, which is S initial or S at the time 0, 300 gram per liter. So we can write 50 into 0.3 into 300 into 10 is your batch time. So if we do so, what would be the answer? Just 20 into 500 is 10,000. 15 to 1 into 300. It is 55,000 grams or 5.5 kg. So this is the total amount of cell at time 10 hours. So now you need cell concentration. They have asked both. Cell concentration at 10 hours is given as your X divided by the volume. The volume at the end of 10 hours, which is we calculated in the previous, which stages has answered is 1000 liter. So to calculate the cell concentration at 10th hour, you have to divide the total amount of cell produced at 10 hours divided by the volume of the medium which would be present at 10 hours. So that is 1000 liters, 55,000. I'm writing in terms of gram per liter. You can write in whichever units the question was asked in. So 55,000 divided by 1000 will give me 55 gram per liter. If in terms of kg, it will be kg per liter means what? It will be 5.5 divided by 1000. So if it is kg per liter, then it would be 0.0055 kg per liter. Okay. So we have a very similar problem next also, but but it has a, we have the very similar problem here. Can you guys start solving it? Same way how we did solve the previous questions. I'll give you 1 minute to write down the given values, then we'll start solving the problem. So let's start by writing down the necessary things. So everything is given here. I need not be writing it again. Let's start straight to the initial culture volume. How we have been calculating is, what was the initial culture volume, which we have been calculating all the time. V is equal to V naught plus Ft. Now the trick is here. It's been asked, the question was to calculate the initial volume. This is V naught. So rearrange the terms. V minus Ft gives you V naught. So let's start putting things together. F is given as what? The feed flow rate of 4 meter cube. And what is given as V? The liquid volume is 40 meter cube. At the end, after 6 hours, the liquid volume is 40 meter cube, it is told. So V naught is equal to 40 meter cube minus 4 meter cube per hour into 6 hours, they have told already. So what is the answer? 40 minus 6 4 so 24 gives you 16 meter cube. So the initial culture volume is V naught is equal to 16 meter cube. So again, what is the concentration of substrate at the quasi steady state condition? Same way, how did we solve this? S is equal to D, the same formula. Let's start putting it together. S is equal to dKs divided by mu m minus D. So now we don't know F, D. So first what should have been done? D is equal to F by V, which is F is given as 4 and volume is given as 40 meter cube per hour. This was meter cube. So 4 by 40 is 0.1 hour inverse. D. We have calculated D. Now just in like put it in this. D is 0.1 and Ks is given as how much? Ks is 0.15 and what else is we need? Mu max is given as 0.35. This is 0.15 divided by 0.35 minus 0.1. What would be the answer? 0.1 into 0.15 is 0.015 divided by 0.35 minus 0.1. This is 0.0606 kg per meter cube. This is the substrate concentration. So we have calculated the concentration of substrate. What else we need to calculate? What is the concentration of cells at quasi-steady state? We have been solving. How we have been solving? We have been calculating using this amount of cells formula and have been uh, coming in terms with by dividing it by the volume. But here you have been given a term called maintenance. Read the question carefully. It is telling that the culture produces a byproduct of energy metabolism. So it is linked to energy metabolism. So you cannot use the same formula as you have been using before. So what would be the formula? So we know when we were doing substrate balance, you would have come across this. So here the product and specific product formation rate is 0. So we can nullify this term. So if we do so, ds by dt is equal to d si minus s minus mu by y-axis plus ms is the maintenance into x. So we know that at quasi steady state, ds by dt will become 0 and your mu is approximately d and the substrate is less than the initial substrate. Therefore, if we substitute these things here, 0 is equal to d dsi because this term has become 0 minus d xs plus, I'm substituting mu is equal to d ms into x. So if we keep x in one side, x is equal to dsi divided by d y-axis plus ms. Now substitute the necessary things, which is x is equal to 0.1 is your d, our inverse, and SI is 80 kg per meter cube. D is again 0.1 our inverse divided by y-axis is how much? It is given as 0.23 kg per kg. 0.23 kg per kg and the maintenance is 0.135 kg per kg hour. So if we do so, we will get the concentration. Let's calculate. 0.1 divided by 0.2343 plus 0.35. It's around 14.05 kg per meter cube. So this is the cell concentration at fast steady state. So now we are asked what mass of cell is produced after 6 hours of fed batch operation. So we need to calculate the mass. We know that xt is equal to x into v, 14.05 kg per meter cube into 40 meter cube is the volume. If we do so, it will be coming around 14.05 into 40 meter cube. So it is 562 kg of biomass required. So this value is the mass of cells being produced after 6 hours of fed batch operation. And what is the before the batch fed batch has started, how much would be it is? So to calculate that, so at the start of fed batch, V naught was how much? It was 16 meter cube. We have calculated the initial volume. The cell concentration is 14. So x is equal to x into V is 14 gram per meter. In terms of 16 meter cube, it is 224 kg was there. At the end, this is at the start and this is at the end. So during 6 hours of operation of fed batch, how much is produced? Which means 562 minus 224. How much would be it is? It's around 338. So during 6 hours of fed batch, 338 kgs of biomass is being produced. If only asked for after 6 hours, this would be the answer. During 6 hours of fed batch, this would be the answer. And at the start of the fed batch, how much would be produced? Amount of cells would be produced. The answer is 224. That's all. We are done for today's class. If you and anyone of you have doubts, you can ask. Otherwise, you can leave the meeting. Is there any doubt?
Thank, thank you, ma'am.
Yeah, thank you. Thank you, Prasanna.